All right, so now we're up to format strings, and this is one of the more bizarre defects of C. You might have noticed that everything that's happened to us here is all because of C. The strange defects of C is what caused all these memory corruption vulnerabilities, and this one is pretty mind-boggling. So I've downloaded a program here, and let's take a look at it. It's ED204. Just a moment, I got to find my shell. All right, there's my shell. I don't need this one anymore, but this one is good. Let's make it big again. Okay. ED204.c is there, all right? So let's just cat it. Okay, so this one here, it just has a main routine. There's no subroutine. And it has a string copy where it copies the command line argument into a buffer that only has room for 1024. So by the way, it has a buffer overflow vulnerability, and you could try exploiting that, and that would be fine, but that's not what we're interested in doing here. It has a second vulnerability, which is more interesting. Now you may remember a correct printf statement is supposed to look like this. You print f, then you're followed by the format string, which would have control fields here like %s where a string goes, and then you put the variable to print here, and it would put it in that format place. So that's the way printf is supposed to look. But for some reason, don't ask me why, C allows you to do this. You can print with no format statement. Now that might seem okay, because it will just print with some kind of default format, and maybe it's okay if you're kind of sloppy and you don't really care how your data is formatted, but it turns out to fail in a spectacular way, which is what we're going to see. So let's run this program. What this program does is it just takes a command line argument, copies it into this thing called buff, and then prints buff. So it just echoes back what I put in. So ED204, if I put in nothing, it tells me I need a string. So if I put in hello, it says hello. So that's not very exciting. And I know if I put in more than 1,000 characters, I'll get a buffer overflow. But what's more fun is to put in stuff like this, %x. Now, what do I get? I get some weird hexadecimal junk. Now, in order to understand why this works, you have to think about what we saw before in the assembly code. When you do a function call in assembly code, it is several commands. You call the C library command, printf, and the printf command looks on the stack for the variables that were passed to it. And it is the responsibility of the programmer to push the variables on the stack first. So if you call it, and you only have this much of the command, where you have a printf, and then you have a string with a format in it, it expects another variable. Now you could call printf with just one parameter, like here, but then that should just be a fixed string that you print without format specifiers. If your format string contains format specifiers, then printf expects another variable on the stack. But the way C works is it just translates your commands one by one into assembly code and runs them without checking for validity. So when it executes this command and buff contains a format string, it goes and fetches the next value on the stack and uses that for the argument. So this is an information disclosure vulnerability. I am seeing data from the stack that the developer did not intend for me to see. I'm peeking into areas of memory that are not my business. And you can peek deeply into them. You can put a bunch of these, %x, %x, %x. Now I'm seeing 4 32-bit words up the stack that were not intended for me to see. Okay, so that's fine. Now, here's another piece of complete madness from the developers of C. I can put %n instead. Now I get a segmentation fault. So this format string allowed me to read the contents of memory. This writes to memory. I have no idea why they gave us this format specifier, and I programmed C for years and I never used it or even knew it was there. What %n does is, what %x does is it takes the value of a variable and prints it. What %n does is it takes the value of a variable interprets it as a memory address and writes to that memory address. So I can now do targeted writes to memory. And the number it writes there is equal to the number of bytes that printf has printed so far in this command. So I don't know what this is for, some other kind of formatted printing that comes out of this. But anyway, it means I can now look on the stack to find memory addresses. And if I can find an interesting address there, I can write to that address. So here I have information disclosure, where I can read data. Here I have the ability to alter memory to some extent. Now they might think there's limitations, although we're going to get around them. I must say, it's just up to your cleverness. One of my students went off and developed the Check-Rein Exploit. We didn't learn that much from me about iOS, but he was an iOS expert, so he took this course and then he started working in iOS, and he found a flaw that made it possible to write a single byte during boot up, and that byte had to be 0. And he totally took over the iPhone with that. That's right. Think of a Monty Python sketch where they say, attack me with this banana. Be as vicious as you like. If you're smart enough, even a very limited attack can be enough. In this case, we're going to succeed pretty well. So the next question is, are we stuck with just the memory that we find on the stack, or do we control it? Well, command line variables are put on the stack somewhere. So somewhere on the stack is the data I put there. So what you can do is put in AAAA as a test value, because we'll know when we find it, because it'll look like 41, 41, 41, 41. So if we run this one, then notice there it is. This is under my control, and the data I put in is on the stack somewhere. It turns out it's 1, 2, 3, 4, 5. The fifth word on the stack is equal to those 4 bytes that I put there. So now I can control a value on the stack, and I can write to that memory location. So we are gaining control of the machine. Now, if all I can do is a write, how do I take over the machine? Well, there's a lot of places you could write that will eventually end up in the instruction pointer. If you can find a return pointer on the stack, you could write there. But it turns out that there are cooler places to go. If I go here, if I do GDB -Q for ED204, and I look at the assembly language. Okay. Here is where it calls printf. And notice it pushes 2 things on the stack before that. So one of these are the parameters, and then it calls printf. All right. It's going to call printf, and then later on, it's going to call string copy. Here's exit, there's printf. Okay. Now, I want to go to the +115. This printf is where the format string vulnerability is. Now let's take a look at the source code to orient ourselves here. Here we go in the program. It's going to print just a usage message. Now that was this printf up here. And that one is not important to me right now because that one is not exploitable. Then it's going to do a string copy and then another printf. This is where the vulnerability is. So I just look on the right, I see here's the string copy, here's the printf. So this is where the format string vulnerability occurs. And after that, it calls putchar to print this single character and then exit. Okay, so the reason why I did this was to show that after the printf, it calls exit. The reason that's important is because I can write to the address of the system library call for exit. You can write to these procedure linkage tables and global offset tables. Those are pointers used to find C library routines, and you can hook them. This is how rootkits work, at least the older generation of rootkits. So you can use objdump, a common Linux utility, to see what's in your file. And if you use -R, it gives you the relocation records. So if I do that on ED204, it tells me these are the functions used by this program, and here's exit, and that is the address of the relocation record for exit. So the address in that 32-bit word right there is used when it tries to execute this command to call exit. So if I write some other address to that location, I will gain control of the instruction pointer. So that's good, clean fun. So to do that, all I have to do is remember when I put in let me go back up here. Okay, when I do this, I put in A's and then %x, 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 %x. And I've added some dots so I can see it more clearly. So those 4 A's end up over here on the stack. So if I want to write to this exit location, I have to replace those A's with these 4 bytes in reverse order, just like we did before. And then I have to have %x, 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 %n. That will read the first 3 and then write to this one. So that will write to this address. So I can do it in the debugger. And now I can examine that address. This will give me the current location, the current contents of that address. And I somehow didn't get the whole thing. x/1x. All right. I got to have a space. And I got to have a 0x in front of it. All right. This is the actual address of the system call to exit. Now I'm going to write there by running with this crafted string. This is 0804A014, which is this address. It's going to be the 4th object on the stack, or the 5th anyway. So this is going to end up here. So I do %x, %x. I read 3 things I don't care about just to get to the 4th one. And then I write to that location. So after I do that, it's going to crash with 1B in the injected instruction pointer. So I did cause it to crash now. I wrote something. Now I wrote a small value 1B, which is 16 plus 12, because it's just equal to the total number of characters printed to that point, which is not a very big number. So that's what happened. And now, if I want to control it in more detail and write a 32-bit word, there are various ways to do it. But one way to do it is to do it 4 write operations. Now, I was writing to this location, A014. So I write once to A014, then to 15, 16, and 17. And so I write 1 byte plus some 0 bytes, then 1 byte plus some 0 bytes. These 4 write operations will take effect here. These 1, 2, 3, 4 %n commands will write to those locations when I print this. So that's how you do it. Let's get out of here and cat f1.py. So I have 4 addresses to write to, and here's my format string. And so I put in those 4 addresses, and then I write with a format string that'll do 4 write operations. And that will write to each of those bytes. So let's check that this is going to run, F1. Okay, it runs. Oh no, looks like I had the same problem I had before where I don't have the right shebang line. Yeah, Control K will get rid of that. All right, there, now it prints. I needed to have some junk to get there, then, all right. I added this stuff here. So it prints a word and then a spacer word, which is why my format string has %n and then %x, and then %n and then %x. So it prints some junk, but it does execute some %n. So that should work. Let's go into the debugger and run with f1.py and examine that variable. Okay. And this is what's in the extended instruction pointer now, 37, 3F, 47, 4F. That is the 4 write operations. That's the address I've injected. Now, I didn't inject any good address that would lead to any real code. I injected just a garbage address to see if it's working. And I did get that address to go in there. And you see it's counting up by what looks like 8 bytes each time. This is the number of bytes printed so far. And we just printed 2 32-bit words. So that's 8 more bytes. And then the next 8 more bytes and 8 more bytes. So now I have control of the instruction pointer, sort of. But so far, I'm just putting garbage in the instruction pointer. So now I would like to hit a specific value in the instruction pointer. And the point is, when I'm writing, I've been writing small values, but I could just print a lot of extra characters to print hundreds of values. And if I wrap over going beyond 256 characters, then I will be able to hit any value I want in the first byte, as long as I don't care about the next byte, which is going to get overwritten anyway. So if I leave there and look at f2.py, here I have the same 4 addresses to write to. And now here's the bytes I wish to write. AA, BB, CC, DD. Again, they're still garbage bytes, but I want to prove that I have control of the values we're writing. So now I calculate the number of extra bytes to write as 256 plus B1, and it turns out that 30 was the amount of bytes of overhead printed no matter what I did. So I just played with these values until I got it right. And now I build this format string. I put a number before the X, so it'll be that many characters of hexadecimal. So it will extend the hexadecimal fields for one of the things I'm printing out to beyond 256 characters, just to make a lot of characters there. So this is going to have big gaps of white space in it. If I run this one, it's going to, this format string is going to tell it to print a hexadecimal value, but use 378 characters to do it, and then 273 and so on. But anyway, that should work. So let's try that one. I'll run it in the debugger. All right, and then I run it. All right, and see it has these big hundreds of bytes of blank space before some of these to make room. And now you see the instruction pointer contains AA, BB, CC, DD. So now I'm able to add any number I want into the instruction pointer. So now I've achieved the same place we were with the simple buffer overflow. I can control the instruction pointer and point to anywhere I want to go. So now we just have to put in shellcode. Now, before I bother generating real shellcode, I'm going to put in fake shellcode, which is just 100 bytes of NOP and 250 bytes of CC, which is break. A break will just stop execution and return to the debugger. The reason I do this is to see if I can execute the code I inject. As we're going to see, there's 2 major defenses that are going to get in our way. Address space layout randomization means everything is moving around and we can't find where the code is. And data execution prevention is the next one, which means that even if you inject code, that segment of memory is not executable and you can't execute code. So rather than bothering to use real shellcode, I'm going to use NOPs and a break to see if the NOPs will execute. If you are in a non-executable region of memory, you cannot even execute a NOP. It will just not do anything. As soon as you try to execute code, it will just stop. So that's F3. Get out of here and look at F3. Okay, and so F3 has got the same 4 addresses, the same fake address here. Then it injects all this stuff. This part here changes the address that will eventually end up in the instruction pointer when I exit. And then after that, since I'm on the stack, my data is going somewhere on the stack, I just put in my NOP sled and shellcode over here. I don't really know where it is, but I can find out with the debugger. So if I run that one, which is F3, looks like this. I've got this junk stuff. Then I have these long hexadecimal format strings to print things. And then after that, I've got a whole bunch of NOPs, which is my injectable code, and then CC, which I'm not sure what that looks like. It might be printing as the same funny looking character there. So I put this in the debugger and I run. Okay, and now it crashes with AA, BB, CC, DD. And if I examine that location, 0x0804A014, I gotta have X1X and then a space here. There, you can see that is the pointer that points to the exit system call, C library call, and this is the thing I injected, A, B, C, D. So let's look at the stack. If I examine the stack, I can just X 200X ESP, make my window a little bigger to make this prettier. Let's do that again. There we go. So let's look at what's on the stack. It's got, here's my NOP sled that I injected. Here's all those CCs of breaks. So now I can just pick an address to jump to. So I just pick an address in the middle of the NOP sled, like this one, for example, and that's what I want to put in instead of AA, BB, CC, DD. So when I did it in my instructions here, I didn't pick it at this point. Now there's another problem, testing for bad characters. This held me up for a long time when I was first learning to do this. You have to find the bad characters and remove them. Remember before, we used MSF Venom, and we used only letters and numbers to avoid bad characters. In this case, we're going to do it in a fancier way. We're going to avoid bad characters, so I don't think I'll do it live. But it turns out that bash command lines, if you have a command line parameter, which is what this is, you have the name of a program, then a space, then the argument, then a space would break it, a tab, line feed, carriage return, and a null byte. So there could be a lot of them. So what you can do is just make a loop that will try injecting all kinds of characters and see if it goes in. So I think this is the one that works. Yeah. So let's run this one. This is bad.py. It took me several tries to test characters, but let's see how this works. I'll get out of here, quit, yes, nano, bad.py. All right, so this just, remember we had a NOP sled and then shellcode of CCs. Here I'm just gonna have a NOP sled and then accounting through all the possible characters, except for the ones I'm skipping, 9, 10, 13, and 32, and I'm skipping 0 also with my loop. So let's save this. And chmod plus X bad and run it to make sure it's going to run. And it isn't because, again, I've got a bad character to start. Get rid of that. Okay. Now make sure it'll run. Okay. So that looks right. So now I run it in the debugger, but I want to put in a breakpoint. So I do a GDB. Now I disassemble main. Remember, we talked about this before. This print statement is harmless. It's the usage message. This string copy, and then this printf statement is the one that has the overflow. So I would like to break after that statement and before the exit. So breaking at this address, main plus 115 would work. So that's break star main plus 115. Okay, now I can run, taking the output of bad, and it's going to print the junk out and then hit the breakpoint so it doesn't crash. And now I can examine the stack to see what's going on. And I can see here's my NOP sled. And the interesting thing here is, did it all get on there? So here's the end of the NOP sled. Here's the 0, 1, 2, 3, 4, 5, 6, 7, 8. Then I didn't print 9 or 10 because that was tab and line feed or something like that. Then B, C, D was a carriage return, so I didn't print it. Then I got 10, 14, so I can just look. I have 18. Then I skipped 20 because 20 was space. And then I got 29, 39, 49, 59. You just look down here to see if it all went on. I got 99, A9, B9, C9. And I went right up to F9 and then FF. So all the characters from 1 to FF went in. I have now found all the bad characters. And if I had a bad character in there, it would only inject, like if I had left the 20 in there, it would only have injected to this point. Then the 20 would have broken it, and all this would not be injected. So that's how you test for bad characters. It's kind of annoying, but you have to try until you find them all. Although after a little experience, you sort of get used to what they usually are. All right, so now I know I have to generate shellcode, and I have to avoid all these characters, null, 9, A, D, and 20. So I use this command to generate shellcode MSF Venom. This is how you dodge bad characters. And it turned out that I had to use some of the advanced options to make the exploit more reliable so it didn't crash. Shellcode is very fragile. Any kind of networking problem often makes it crash, and it never gives you error messages or anything. So if you use the advanced options in Metasploit, you often find that they're needed. That's why they're there. So this gives me an exploit that's 120 bytes in size. So that's F5, and I think I've got my F5 already made here. Yeah, so here's the final exploit file. Yeah, where now I've got a real address here that hits the NOP sled, FFFFD11C. It has to be backwards, as always. And here I've got the actual egg, and there I got a NOP sled. So this should do it. Let's give it a try. Run it in the debugger. And let's put in that breakpoint again. Wonder if I can use up arrow. I can't. Let's just copy it from up here. Thought I had it. Well, be that way. I'll just find it again. All right, let's disassemble. Main. And this is where the overflow happens. So I want to break at main plus 115. Break star main plus 115. All right, now I'm going to run, and this is called F5. So I run, taking the input data from F5.py. Okay. It runs, it prints out this junk, it hits the breakpoint, and now I can look and see what happens. So I can examine the address that is going to go in the instruction pointer here. That is the address of the exit routine. So that's going to go to FFFFD11C. And if I examine the stack, I'll look at 100 words of the stack. FFFFD11C is here. So it is going to hit my NOP sled, slide down the sled, and run my exploit. So it looks pretty good. So let's continue. And it exits normally without crashing. And because I put in that prepend to fork, it launched a new process. And we should be able to see that process. We can quit from the debugger and now do SS minus pant again to look at the network sockets. And we'll find that there is a process listening someplace back here. Yep, listening on 4444. That's what I did. So now I've got it. I can connect to it and see that it works. That's giving me a shell. I can do net connection 120 and netcat 127.0.0.1 and I can do who am I and print working directory and so on. So now I have a command shell on a listening port, the same as before. So I've proven I can run code I injected. So I'll exit from this, and that will close that process. So that's the game there. That is a format string exploit, which is pretty strange. They're actually pretty easy to exploit once you get used to this, but it is a little bit mind-bending to use those strange format string commands. All right. So I'm going to